Thank you for the introduction. I'm Merve, and I have recently finished my PhD, hence I am shamelessly using my new title everywhere, on every slide, as much as I can. And it hasn't been long since I joined the data science team at LV. So LV is a financial services provider with over 5.8 million customers. We're mostly known for our car insurance, but LV is actually offering a wide range of general insurance products, as well as protection and pension policies. We are selected the most recommended insurer by YouGov, and for the last 6 years, since 2013, Moneywa is the most trusted insurance provider. But what makes me excited as a data scientist to work for LV is the wide range of data that has been generated across the business, hence fed into our team, and the breadth of the projects that we're working on. So wide range of data in all sorts, from text data, time series data, and image data, have been generated across businesses. But it's not something surprising in this day and age. Unprecedented amount of data has been generated across the world around all the businesses every day. But we need to find a way to gain insights and extract meaningful information from these large data sets. And this led to the creation of the field machine learning. So in machine learning, creating data representations is the key. So data representations are known as features, and they help the algorithm to identify similarities and differences between different categories. And today I'll be mostly focusing on deep learning. And deep learning approaches, algorithms, aim to reduce the manual intervention in creating features given the dataset. So they extract raw data as an input and try to extract some features. They are composed of different levels, and they extract the features in a layer-by-layer hierarchical manner given the raw input data. So every layer is composed of simple units called neurons, and these neurons are trained to extract features in a hierarchical manner, and they learn the abstractions and representations of the data. So I said deep learning structures are hierarchical. So as we move higher up in the layer, the features are identified through their similarities to the other features extracted in the previous layers in the network. So what I mean by that, let's take an example. Say we're trying to train a network to identify an object. So the initial layers would identify more custom features, such as edges, which can be common across different images. And as we move deeper in the architecture, it would start identifying mid-level features that are formed by the lower-level features, like motifs formed by the edges. And as we move along, then it would be parts of the object, and eventually it would be the object itself. Exploiting the different variety of the data we are sending to the deep learning architectures, there are several different versions. And the simplest one is probably the feed-forward neural network and multi-layer perceptron. I think they're quite crucial because it won't be wrong to say that they form the building blocks of more sophisticated methods. Say, for example, to analyze sequential data like text data, state-of-the-art methods is the recurrent neural networks, and multi-layer perceptrons can be accepted as the conceptual building blocks. The other field that benefits from these architectures is analyzing images, coming up with an automatic way to extract information from images, which can sound like a trivial task for us humans, but it has proven to be complicated for computers. And one of the widely used methods for that case is the convolutional neural networks. So CNNs are can be thought of as specialized deep learning architectures to accept input data that has a lattice-like form. So they're specialized to analyze data that comes in forms of multiple arrays. For example, a color image, where we have three color channels, red, green, and blue, with a 2D grid of pixel values. So this is a toy example showing the difference between a multi-layer perceptron and a CNN. So CNNs arrange their neurons in a way that they can convert a 3D input to a 3D output. So they're very powerful, but they're not new. They've been introduced nearly 3 decades ago, but it wasn't until 2012 they had their major breakthrough, thanks to the increased computational power of the computers, easily programmable GPUs, and the increased training datasets. Like, for example, the abundance of the online data that can be used as training and crowdsourcing platforms that we can actually outsource the labeling process. So CNNs are widely used, and thanks to the programming packages, they are quite easy to implement. Hence, most of the time, they're accepted as a black box. But in order to customize them better and make the most of these powerful architectures, we need to have at least some sort of understanding of how they work. And I think it starts by understanding the building blocks of these architectures. So the first layer of a CNN, as the name suggests, is the convolutional layer. And let's start with understanding what a convolution is. And let's do it with a toy example. So imagine we have a 4x4 matrix, forget about the images, as an input data, and we have a 3x3 convolutional filter. Disclaimer, for simplicity, I'm not taking into flipping rotation into account. If you know what I'm talking about, just don't please pick me up on that. It's just for simplicity. So we place the convolution at the initial position, and it's just simple dot product. We multiply each element with the element that it overlaps with, and then we sum it over, and then report the output. So convolution is simply a function of an operation of mathematical functions. And then we shift the filter to the next position, and the amount of this shift is called stride. In this case, it's just stride 1. And then we repeat the same process, and we report the output. So this would give us the 2x2 output. And it won't be wrong to say the output size is then determined by the input size, the size of the filter, and the amount of stride. But there's another way to control the size of the output, which is a simple trick called zero padding. So if you want to have a better control of the output, for example, if you want to have an output the same size as the input, you can just artificially expand the size of the input by adding zeros around. This is probably not the best example, but it's just to visualize how zero padding works. So by just padding 0 around the original image, which is shown with a bold box, I managed to expand a 4x4 image to 8x8, not image, matrix, sorry. So convolutional layer consists of lots of convolutional filters. So each convolutional filter will return an output, which is also called an activation map or a feature map. So we can think of it, again, as like this simple example. The initial layer, imagine we have a very, very teeny tiny data, 4x4x3. And then by using 3x3x3 filter, we can just get a 2x2 output, which will be the feature map of this filter. And then the output of the entire convolutional layer is formed by stacking those feature maps. So we'll have as many feature maps as the number of filters. So convolutional operation within the convolutional layer brings CNN a few advantages. And let's start with the local connectivity. So again, we have that 3D image as our input. And imagine instead of a CNN, we have a multi-layer perceptron. For multi-layer perceptrons, they're fully connected. So what I mean by fully connected is every input unit is connected to every output unit. So what is the input unit in our case is a pixel value of an image. So this is not a big image. Let's say it's 200 by 200 times 3, 3 being the color channel. So if we have a multi-layer perceptron, for one single output unit, we need to have 120,000 weights to learn. But if we use CNNs, the convolutional filters would be connected to local patches of the input image. And for one single output unit, imagine our filter size is 15 by 15. In this case, we only need to learn 675 weights. So that's a good improvement. That reduces the number of parameters vastly, which shows that MLPs actually don't scale well with the large images as we increase the image size, because it would increase the computational time and it would increase the storage requirements to store the expanding number of parameters. So local connectivity is good, but imagine the example I showed you when creating feature maps. So if we have input size and filter size as this setting, the output size would be 57 by 57 times the number of filters, or the activation maps. So in this case, even if there are local connections, what the network needs to do, take the filter, connect it to a local patch, learn 675 weights plus a bias, and then move it to the next location, learn the same number of parameters, and move it to the next location, and keep doing the same. So it's, again, not very feasible. And here, CNNs actually make an assumption. They say if calculating a set of weights in one location is important for one spatial location, it would be important for another spatial location. So what that means is instead of learning a set of filter weights at each shift, they just learn one set of weights, use it to sweep through the entire set of image, create the feature map for that filter, and skip to the next filter, learn its weights. So that reduces the number of parameters greatly again. It does not have any improvement in the runtime, computational time, but it reduces the storage needs greatly. Another advantage that parameter sharing is bringing is called translation invariance. So translation invariance means that if you make a small change in the input, you would see the change in the output. So what were we doing in the convolutional layer? We were trying to map the input image to some feature space. So for example, if we move an object within the input image, its representation will shift, will move the same amount in the output due to the translation invariance property. So it's very useful when we have repeating patterns and objects within an image that we want to actually identify. So within the convolutional layer, thanks to local connectivity, parameter sharing, and translation invariance, CNNs can identify intricate relationships embedded in the underlying data. So convolutional layer is where the linear operations take place. So they are commonly followed by a nonlinear layer. So we have our output computed, and this output is basically passed to a nonlinear function called activation function in this nonlinear layer. And the activation function in the earlier papers were mostly a hyperbolic tangent, but in the recent studies it's been switched to a function called rectified linear unit, which is a simple function that would choose the maximum value between 0 or a given value. So after the nonlinear layer, another important building block of a CNN is the pooling layer. So the pooling layer summarizes the nearby features into one by using a chosen operation. So what do I mean by that? So let's think we have this 4x4 matrix, and we want to perform pooling operation on this. We want to summarize these features. And for this, let's first pick a max operation. So what the pooling layer does is takes this matrix, picks the maximum value, and then returns it. So what happened here is we transformed 4x4 input to 1x1. So again, we reduce the number of parameters here. Another operation can be a sum operation, and then you would sum all the values within that frame and summarize it. So pooling layer summarizes those features quite nicely, and this summarization creates certain advantages, which makes networks, CNNs, robust to small changes, because, for example, we pick a maximum operation and make a very small change in the input frame that we want to summarize, and that's not even the change in the maximum value, so we won't be able to see that change in the output if that change is very small. By reducing the number of parameters, it helps avoid overfitting. And because it's also summarizing and outputting a fixed number of, creating a fixed number of output, it's also good with tackling different input sizes. So these are the main building blocks of CNNs: convolutional layer, nonlinear layer, and the pooling layer. And we can create different architectures by stacking these layers differently before we add the fully connected layers to the network. So now we have created our network. We need to train it now. So training the network, we should first think of what are we trying to do with the network. So let's again pick a classification example. We have an input image, and we have a set of categories that we want to classify that image into. We pass the image to the network, and the network will output a set of scores, one per category, each indicating how likely that image can be classified into that category. And in order to check whether the network did a good job, we then compare it with the actual categories. So this training is done in a supervised fashion, as you can see. So we're comparing what we expect the network to return and what the network actually returned. And this difference is basically the loss function. And then the network would aim to minimize this loss. So it would adjust its weights accordingly just to minimize this loss function. Before I switch there. So there are different optimization techniques to minimize the loss function. For the sake of time, because I thought I won't be able to summarize them, I would just mention some of the names and go to the next step. Some of them can be as easy as the stochastic gradient descent, or a bit more sophisticated adaptive methods like ADAM optimizers. Okay, so we optimize the weights. We are trying to come up with the best set of weights that would minimize the loss. But another important part of the training process is the training dataset, because that is the only data, the only knowledge we make available to the network to train. But thanks to the abundance of online images and the crowdsourcing platforms, now we can create large-scale image datasets. And some research groups around the world are actually making them freely available, which is very good. And I just want to talk a bit about those image datasets. So one of the famous datasets is called ImageNet. Have you heard of it? How many of you can I see? Okay, less than half. Just for the ones who don't know. So this one is based on WordNet hierarchy. So imagine there are like words and phrases that are stored in a hierarchical manner. Like, for example, if you look at this example, the the top level is mammal, and then if we go, it becomes more specific to like carnivore, dog, and then even like the breed. So why am I telling you this? Because the categories within the ImageNet are formed by using the WordNet hierarchy. So what they did was they sent lots of requests to multiple search engines by using the words and phrases within the WordNet hierarchy. And they formed a large set of images. And then they used the platform called Amazon Mechanical Turk to have these images labeled. So Amazon Mechanical Turk is a crowdsourcing platform. There are paid users, and you can basically outsource your labeling job. And it can be done by multiple users, and it is quick. It's just you need to have resources for that. So ImageNet focuses more on the objects. But what if you want to classify the scene? So there's another database called Places Database for this case. And you can see like the categories are a bit different from ImageNet, so whatever your need is, you can pick and choose, and they're all freely available. So ImageNet and Places databases are category-based. So what I mean is each image is labeled by a single category. So another research said, well, we might need some more to have a holistic representation of the scenes. And then they introduced this attribute space where there are no clear boundaries between different attributes. And then they created 102 attributes, and it's called Sun Attribute Database. So this is also freely available. So these datasets are great. They are large. They have a good number of categories within them. They are clean. So they're great for end-to-end training of a network. Because, let's admit it, CNNs are powerful, but they're powerful in end-to-end training when we actually pass them good data sets. But what happens if you don't have enough resources to create training data at scale, and you have a different problem than these? So the good news is CNNs are adaptable. So you can take a network that has trained on one of these large data sets and transfer the knowledge gained through that training process to your needs. You can do it in two ways. One of them is called transfer learning. You would still ideally need a GPU to do that, but it's not as intense as training a network end-to-end. So how it works roughly is you get rid of the fully connected layers of a pre-trained network. You take the convolutional chunk, and you freeze the weights. What I mean is during the training, you don't update the weights anymore, and you add some fully connected layers of your own, or some convolutional if you want. And then you run a few epochs with your training data, and then unfreeze some of the weights from the convolutional chunk, preferably in the later steps, and then keep training it for a bit longer. And then you'll hopefully have your pre-trained network justified to your needs. So that's a good way to repurpose a pre-trained network. But what if you don't have these resources, or you just want something really quick? Well, you can use CNNs as feature extractors. Have you ever used traditional image features like SIFT or SURF? Can I see hands? OK. So they are like handcrafted features. And then you send those features to train a classifier, like, for example, a linear SVM. So you do the same thing with the CNNs. You take the output from preferably one of the fully connected layers, and then treat it as a feature vector, and then send it to a classifier to train a classifier. And you can do this on a CPU, which is quite lightweight. So you can still train as if you have a handcrafted set of features, but you use the powerful feature extractors trained on a very large set using CNNs. So CNNs are powerful, and they are widely used, especially in analyzing images. They have a wide range of applications. And we are also using CNNs at LV. But how are we using CNNs? So we have a project that we're currently working on, which is to estimate the repair cost of a car automatically given an image. It is quite a hard task. It is even hard for us humans sometimes. So we decided to approach it by breaking down into smaller, more manageable pieces. Say, for example, which part of the car is damaged, what type of damage is present, how bad is the damage, and basically, what part of the car is damaged, what orientation, and so on and so forth. And as I mentioned, the importance of the training sets, it is also quite important in our case. And it might have been like the most difficult part of the project. Because we decided to split it down into smaller chunks, we needed to make sure what labels to collect and formalize the solution at quite early stages so that we can actually start collecting training data and do the labeling process. There were quite a few questions that we asked to ourselves to help us guide through this problem. So what image labels should we ask for? What can be helpful? And how many images do we need? Who is actually going to label these images? Are we going to give the image to one person to label? Are we going to make multiple people label the same image? And what happens if they actually disagree on the label? And also, how can this actually be scaled given the business needs and the restrictions we have? So what we did is we did create an in-house image labeling app, and then we gave a bunch of damaged car images to our engineers because they are the domain experts to collect the labels, so they need to answer a set of questions. Hence, we collect different labels for the different parts of the project that we are treating as different problems. And hopefully, we have a clean data set, clean training data set, so we decided to pick up on the transfer learning approach. Take your pre-trained network and then transfer its previous knowledge to answer to our needs in this problem. But here we again had some resources to do the labeling, we had the images. What if you don't even have those resources? What if you don't have the time? What if you don't have the money to have anything collected and labeled? So I said it wasn't long ago since I finished my PhD. And throughout my thesis, I used CNNs quite a lot to analyze social media images to quantify human behavior. I know it's quite like a broad topic. I'm happy to discuss more about it. But I had several different projects under this broad umbrella. And one of them was tracking protest outbreaks by using Flickr pictures. So with my supervisors from University of Warwick, Tobias Price and Susie Moat, we decided to focus on pictures taken and uploaded throughout 2013 and uploaded to Flickr. And this is more than 20 million pictures. So the first hurdle, we had to come up with an automatic way to group them as protest-related or not protest-related. And we don't have a training data. And we didn't want to wait that long to collect the data. So what we did was we turned our faces to the search engines. So luckily, Bing Image Search provides an API that enables you to download the top 150 image results. So 150, okay, it's still good, but not enough. So we created an automatic search, which it has a name of a country, followed by the word protest. And then we iterated over a set of countries, and this basically gave us around 20,000 positive training data set. And in order to create a negative training data, we updated the search phrase to the name of the country, things not protest. So not here is important. It's like a keyword for Bing, saying that do not return me images that are indexed as protest. So we again managed to gather quite a bit of negative training data set. So we knew that potentially the training data sets we've created would be noisy. And it is usually not recommended to use transfer learning when you have quite a noisy training data, because you can mess up with already nicely learned weights. So in this project, we decided to use CNNs as feature extractors. And what we wanted to see was the repeating items that are present in the images. For example, I mean, you tell me, what do you think would be present in a protest image? What would be the repeating pattern? Pardon? Placards. Yeah, placards. What else?
Lots of people.
Lots of people, crowd, yeah. Police, pardon?
Potentially smoke.
Smoke, oh, I never thought of that. Or like policemen, megaphones, the ones I've seen. So we wanted to use a pre-trained network that is originally trained on a data set that focuses on objects, not surprisingly, ImageNet. So what we did is we extracted features from the training data. We extracted using Bing image search and used a linear support vector machine to train a classifier. And then we test the performance on a test set. It was all right, let me put it that way. It managed to detect around 64–65% of the positive test data correctly, but it misclassified more than 1/3 of the negative test set. So what normally is done when you create a training data automatically is to do some sort of pre-processing to get rid of the noise. And one method is, for example, use cosine similarity and remove the potentially images that are potentially like outliers that are not so similar to the rest. But protest scene itself is quite a vague concept, so we did not want to use anything like that to remove the diversity of the training data. So we created another training set. But this time, we used images from Flickr, but the year before, 2012, than our target year. So as a positive training set, we extracted Flickr pictures uploaded with the word protest, either in the picture title, tag, or description. And we did it for the word protest in 34 different languages. So that gave us a positive training data. And then we took this classifier and ran it over that positive training data we created, and some of the pictures were classified as not protest related. And then we were like, okay, let's leave them. They are probably noise. This was the assumption we made. And we just kept the ones that are labeled as protest related. And then we took a random subset from the remaining Flickr images from 2012 and then trained another classifier. So it's like a double training step here. And this actually improved the performance. If I'm not mistaken, the accuracy was around 83%. And we were quite happy with that, and we ran it over the entire set of Flickr pictures from 2013. And let me show you some examples. So the pictures with a blue frame are correctly classified as protest related. And I just want to draw your attention to one point. They are holding protest signs, and the language used on those protest signs are not necessarily the same. So when we started this project, we wanted to create a language-independent tool to detect protests. So this shows that, suggests that we are in the right direction of achieving our goal. And the pictures with a red frame, they are also correctly classified, but they are classified as not protest-related. And the good thing, well, what I personally think the good thing, is there are still groups of pictures but they're not labeled as protest related. So the classifier can, to a certain extent, actually differentiate a normal crowd from the protesting crowd. So I'm not going to talk about the entire project, but just a spoiler alert, our results were in line with the initial suggestion that the photographs shared on social media platforms can improve the estimates of the number of protest outbreaks around the world. So the paper is not out yet. If you want to know more, I'm happy to discuss, or follow me on Twitter. I would probably promote, hopefully, when the paper is out. So CNNs are not only used for image analysis. There are other fields that they have proven themselves to be powerful. They are, for example, used for sentence classification, used in creating recommender systems, or used in speech recognition. And I personally think it is so exciting to see what has been achieved so far, and I'm quite looking forward to see what is next. So today, I tried to a little bit demystify the convolutional neural networks by talking you through the building blocks, a bit about training them, mostly focused on what is available out there as the datasets that you can use if you want to. And then I talked you through some applications by giving examples from the project that we work at LV and a project from my own PhD. So these applications, together with the other applications out there, highlight the potential of the CNNs and how powerful they are to automatically analyze images. But I personally don't think we can embrace their power in full unless we understand these systems, at least at a certain degree. So I have some special thanks to my colleagues, Dapang Wang, that we're working on the repairing cost project together. I used some of his slides. And if you want to hear more about the projects that we work on LV, we have a stand in the foyer area, and we have cookies, edible cookies. And thank you for your attention.